Okay, we're on part 4 of chapter 19, and we're going to discuss interference, wave interference, and uh, the superposition. And before we start, before I get to the lecture, I'm going to do a little demo. I've got my water here; it's pretty much full to the top, and I'm just going to blow across the straw and listen to what happens. You can hear the hopefully you can hear the frequency changing as the straw gets longer. The frequency went lower, and as it got shorter, it went higher. I'll do it again. So what's happening is I'm creating a resonance, and the resonance comes from the vibrations going, bouncing off the bottom of the straw when it hits the water and coming back and forming a resonance. So now let's share um, the uh, PowerPoint, and we'll we'll let me dismiss my my image. Wave interference. Wave interference occurs when two or more waves interact with each other because they occur in the same place at the same time. So we were having wave interference with my blowing across the straw, and it was setting up this interference. The interference can be both constructive and destructive, and we'll study that a little bit more. And also, we're going to discuss the superposition principle. The displacement due to the interference of waves is determined by adding the disturbances produced by each wave. So let me stop the share because I want to use my hands. Let's say you're attending a small concert, and there's a guitar, bass, drums, and piano. It's just a little combo. And as the guitar plays, I mean, most likely it's not acoustic. He's got his own amplifier. Let's say each uh, individual has their own amplifier. Of course, a drummer doesn't need an amplifier. He's pretty loud as he is. And the piano, uh, it's loud enough. He might be mic'd, and it's coming together. Now, what you're hearing, you're not hearing one set of molecules coming from the piano, another set of molecules, compressed and rarefied molecules coming from the bass, and another coming from the guitar, and another coming from the drums. By the time they reach you, there's a superposition. All of the air molecules are combining to give you um, one uh, one wave that is a mixture of all of the waves that you're hearing. That's the superposition principle. It's not individual waves coming at you; they're all summed together. So let's go back to the. Okay, let's read that again. The displacement due to the interference of waves is determined by adding the disturbances produced by each wave. That's what we're talking about. We're talking about the guitar wave and the bass wave and the drum wave and all of the piano wave. All of these are added together to give you one wave, but it has all of these superimposed on one another. Okay, constructive interference. When the crest of one wave overlaps the crest of another, their individual effects add together to produce a wave of increased amplitude. So you can see here, we've got they're in phase. So the crest here adds to the crest here. So uh, you get reinforcement. So you can see how it's bigger. Destructive interference, when the crest of one wave overlaps the trough of another, the high part of one wave simply fills in the low part of another. So their individual effects are reduced or even canceled out. I will add a video on the uh, on canvas where I actually take two speakers that are side by side. Let me. Sometimes I just need my hands to discuss. I have two speakers side by side, and I uh, I'm playing a single tone through them. And as I move one speaker toward the camera where the microphone is, you can. There's a point where you don't hear the signal anymore because they're canceling out. They cancel out as determined by the wavelength of the tone that I'm using. A different wavelength, the spacing between the speakers would be different, but I can move them to where we get cancellation, and I'll include that on the canvas, and I'll probably include it on this video for those of you that aren't in my class and that don't have access to canvas. I'll add that video. Let's go back to the PowerPoint. Okay, so destructive interference. I'll demonstrate destructive interference in that little video. Okay, more examples of wave interference. We see the interference pattern made when two vibrating objects touch the surface of the wad. If you were to take a tuning fork, strike it and let it vibrate and put it in water, you'll see that the water splashes because the tuning fork is vibrating. The regions where a crest of one wave overlaps the trough of another to produce regions of zero amplitude. And a point along these regions, the waves arrive out of step, that is, out of phase with each other. At points along these regions, the waves arrive out of step, that is, out of phase with each other. Okay, that's wave interference. Now, if we tie a rope to a wall and shake the free end up and down, we produce a train of waves in the rope. The wall is too rigid to shake, so the waves are reflected back along the rope. By shaking the rope just right, we can cause the incident and reflected waves to form a standing wave. So you can, if you vibrate this, you can see it's anchored here, so it's not going to move. So as you vibrate it, you have an incident wave and a reflected wave, and they reinforce. You have if you were to do it such that the incident wave and the reflected wave, I think I accidentally touched the forward. Okay, and the incident wave and the reflected wave, they cancel, so you get none. You get a node, and then when it you have the incident wave and the reflected wave. Again, they're in phase, but this time in opposite, and you just get this repeating pattern. I know there's videos of guitar strings vibrating. People put their iPhone in the hole of the guitar and the body of the guitar, and they pluck the strings, and you can see the vibration. It makes the standing wave patterns. But now that's not part of that. Is the artifact of the timing of the camera, but it makes some pretty nice patterns. Okay, let's go on to the second one. Those are the regions of minimal or zero displacement with minimal or zero energy. Antinodes are the regions of maximum displacement and maximum energy. Antinodes and nodes occur equally apart from each other. And basically from one node to another node is a half wavelength. So see, this here is a complete wave. From here to here, that's half a wave. From here to here is half a wave. Only this one is a complete wave from one end to the other end. Okay. Tie a tube or string to a firm support. Shake the tube from side to side with your hand. If you shake the tube with the right frequency, you will set up a standing wave. You can set up a single standing wave. If you vibrate it twice, as fast, you get a standing wave of half the wavelength, having two loops. So this actually is a half lambda, half wavelength. This is a half a half wavelength. This is the entire wave. If you shake the tube with 3 times the frequency, a standing wave of 1/3 the wavelength, having 3 loops results. So you can generate these nodes and antinodes. The peaks here are the antinodes. The zero crossings are the nodes. Okay, I think that's it. The waves on a guitar string, sound waves in the trumpet. These are examples of they're really look nice, or you can draw them out nicely in organ pipes, pipe organs. You can see the standing waves in a pipe organ, or like with my soda straw, you would see, you can kind of imagine what the wavelengths would look like in the soda straw, where there's no vibrations at the bottom of the straw where the water is, so that's an antinode, and at the top of the straw is I said that wrong. At the bottom of the straw is a node, because there's not going to be any movement. At the top of the straw is an antinode, because the molecules are free to vibrate there. Okay, I think that's it for part 4.